Yeah, cool. Okay. So the first question I have is for you guys. Who's using microservices with Node? So that's really interesting because I used to ask the same question about 5 years ago about Node. And it was kind of the same kind of numbers, sort of 5 to 10%. This talk is part of a series that I'm doing about using microservice architecture with Node. So it's kind of a field report as well as being opinionated. We've tried pretty much every variant of this architecture, every variant of different ways of doing things like service discovery. There's an ongoing, I guess, research project to figure out how to build really large-scale Node apps. And what we found, having built a whole bunch of them for a whole bunch of different people, is Node and microservices fit really well together. And in some ways, the reason for that is JavaScript, the language itself. Because JavaScript is so simple, you have so few language features that are designed for large-scale code bases. So it kind of pushes you in a direction of small files and small systems. But I want to start with a little bit of philosophy. So this is the flight deck of the Space Shuttle Atlantis, and this was actually taken from STS-101, which is one of the missions. The computer system that ran this spaceship was completely amazing. Amazing from the point of software quality. So they had like one bug every release, pretty much on average. I think somebody added up how much it cost to build the flight control software, and it was $1,000 per line of code. It's probably one of the most perfect pieces of software human beings have ever written. The problem is that a lot of the software development that we do, especially in our large organizations, makes the implicit assumption that this is the level of quality that we want to reach. And it's kind of unsaid. And in a way, we as software developers are sort of guilty of not asking the business what the acceptable level of errors are in our system. We sort of assume that everything has to be banking grade, fully consistent data, and even banking systems aren't anyway. But we kind of put ourselves through these death marches because we're trying to build software that is this good. And actually, that slows us down and creates technical debt and all that sort of stuff, and gets us wound up when we choose particular frameworks and that sort of thing. There's a different way of building software which kind of feeds into the microservice philosophy, which is it's okay to make mistakes and it's okay to have errors in your system. And one of the most important questions you can ask is, what are the acceptable error rates? How many requests are allowed to fail on an ongoing basis? The microservice architecture lets you measure that error rate, lets you make that decision explicitly. It also lets you move much faster. So building this software for the space shuttle was a very slow process. Most of the time, we need to build software way, way faster. And yes, frameworks like Nodejs absolutely can help. But you still have to implement your own business logic. And that's the difficult piece, because building that business logic quickly and not ending up drowning in technical debt is part of what Node gives us. And when you put that together with microservices, you get a really big win. I'm kind of inspired by this aircraft. So this aircraft is the first human-powered airplane to fly across the English Channel. It was built to win a kind of an X Prize set in the 1950s. And it was 100,000 British pounds sterling at the time. And a lot of people tried for about 10 years to figure out how to get a human-powered aircraft to fly across the English Channel. And this one, the Gossamer Albatross, was the one that won the prize. And the reason it won is because the engineer, a guy called Paul McCready, who built this aircraft, realized that the problem wasn't to build an aircraft that could fly across the English Channel. The problem was to figure out how to iterate on the aircraft design quickly. Because a lot of the teams were spending a year designing an aircraft. They would get into it, it would fly for a couple of hundred yards, the pilot would be completely exhausted, and it would crash. or would never get off the ground in the first place. Paul McCready came up with a system of building aircraft with mylar and aluminum piping that let him iterate the design. He could build up to 3 different designs a day. And once he had that system in place, it only took him a year to win the prize. So you can contrast these 2 different methods. The space shuttle software was nearly perfect. Took a very long time to build. This aircraft wasn't perfect, but it did the job. And that is the underlying philosophy of the microservices architecture. So it is almost a business decision, a trade-off to start adopting this architecture. What do I mean when I say microservices? There's tons and tons of definitions going around. I think it's actually pretty simple. They're small independent processes, lots of them running, hundreds usually. They're communicating via messages, whether that's over Kafka as a message bus or direct HTTP requests or whatever. And microservices are also a component model. And that's an interesting thing that I think a lot of people miss. Building software is about finding ways to reuse what you've already built. Microservices are a really, really good component model. And in fact, in our own work as a consultancy, we found that's one of the most effective things about using them, because they let you reuse code really easily. The reasons for using them: you avoid technical debt. It's the same as the difference between the space shuttle and the Gossamer Albatross. It's really easy to get continuous delivery because you can do partial deployment. That's another fantastic benefit. If you have 50 services running your system, you don't have to redeploy all 50. You make a change to the one service that is affecting the feature that you need to change, and you just deploy that one service. And it lets you build fast, because in changing that feature in that one service, you don't have to care about any of the other microservices. You don't have shared data structures that you're going to infect the other services with technical debt or break them in some way. But there are trade-offs. Right? There's no such thing as a free lunch. Deployment is complex. You have to automate. You don't get away with traditional deployment models. The programming model is pretty weird. And this is where, again, I go back to the philosophical imperative. This is about building systems where there are acceptable error rates as opposed to perfect software. So it's a different way of looking at the world. It's kind of like everybody thought data had to be normalized, and then a couple of years back, people realized that if you denormalize data, that was a good trade-off for getting faster performance. It's the same sort of thing. And the other big problem is services have to find each other. So I have one node process A and another node process B, and A needs to use something that B provides. How do I communicate from A to B? Do I make a HTTP request, and I need to know the IP address and the port number of B? Do I look it up in a service registry? How do I do that? This question is a fundamental one, and it's very easy to get wrong. And if you just treat microservices as little REST servers, and you just have direct HTTP connections, you can end up in a lot of trouble really fast, because you actually end up with very tight coupling. So this diagram, I'll go back to this diagram, is a picture of microservices, but it's also a picture of 2 objects, one object calling a method on another object. And the key thing that's happening here, the really big problem, is identity. A needs to know the identity of B. And in knowing the identity of B, you've created a strong coupling, which is exactly the opposite of what you want, because in the microservice architecture, you want one node process not to be dependent on another one. You want a world that looks like this, where A sends out a message because it needs some sort of resource, and B receives that message somehow, but it doesn't know from where, and acts on it. And now you have a fully decoupled system. I can upgrade A, change B, without affecting anything else. So how does A find B? There's a couple of different approaches, which we've used, all of these approaches, over the years as we started building these systems. One of the first is, which actually works kind of well, especially locally, is just configuration files. You just hard code the locations. Obviously, that doesn't scale, especially for production systems. What a lot of people do, and you'll see Netflix doing this, is intelligent load balancing. So you have a load balancer, you send requests to the load balancer, and it knows where stuff is. Netflix Eureka is a really good example of that. The problem is those URL paths, they're still identifiers. A still knows too much about B. There's still coupling. What about using service registries? So this is things like Console or Zookeeper. That works pretty well. And we've used them a lot in production. Problem is A still has knowledge of service B. It has to say, tell me where service B lives. It has to know that service B exists. What about using DNS? So that's a pretty good solution too, right? Set up a little DNS server inside your network. You can even do load balancing, all that sort of cool stuff. Problem again is A knows the identity of B. A message bus decouples things a little bit more. So instead of A knowing where B is, A is publishing to a topic, and B is listening on the topic. The problem is that topic is still a kind of identifier. It's still a weak identifier. How do I get to this position? Because this is where I start getting the big benefits. And this is where the weird programming model piece comes in. What we found over the years of building these things is that there are two key principles that you need to use. The first one is pattern matching. So when A sends a message to B, it shouldn't post a message to a topic. It shouldn't send the message to a network location or a DNS address or something like that. The system, the network, somehow should look at the message and figure out where it goes. You pattern match on the messages. So if the message has a particular set of properties, you know that it goes to a particular service. That means that A does not have to know where to send B. Something else knows. Transport independence is another important point. All of these methods of transporting messages, direct HTTP requests or message buses or whatever, they actually, in some senses, are independent from the service itself. The service is just sending a message. It doesn't really need to know or care that it has to talk to Kafka or RabbitMQ or has to send a HTTP request. If you're writing a node microservice and you're embedding the transport protocol, you're using request or something like that to make a HTTP request directly inside your code, you're going to end up in trouble because you haven't abstracted away the message transport. What you want are blind messages. Services have zero knowledge of other services. All the service does is emit messages into the world and receive messages from the world, and it doesn't know how they get sent out and how they arrive. This doesn't mean that there's magic, right? The underlying infrastructure has to do this stuff. But from your perspective, as a developer writing business logic, so the code that would go inside the controllers inside Nodal, for example, that code should not have any knowledge of how the messaging infrastructure works at all. So again, we have this problem. How do you do service discovery? How does A know how to get the message to B without knowing where B is? Well, you can rely on some underlying infrastructure to do that, but the underlying infrastructure still has to find out. And we looked at all things like service registries and that sort of stuff. But there's one final approach, which is to use peer-to-peer gossip protocols. They are very interesting. The reason that they're interesting is that your system can be very dynamic. They do have a strange effect, though, which is that every service has universal knowledge. So the only way this works is somehow every service has to be informed of every other service. It maintains a local table. Essentially, it's a client-side load balancer. The nice thing about that, if you imagine a system that works like that, is service A knows where all the instances of service B are. In the underlying infrastructure, the business logic code doesn't know. But A at least knows there are all these different IP addresses. It can round robin, it can do pub sub, whatever. And B knows where all the A instances are, and C and D, and all the other microservices. It's actually a very nice model. It's completely decentralized. It doesn't rely on a central service registry or any trickery with DNS or anything like that. You just have the knowledge and you just send a message directly. The question is, how do you get to that state? How do you get to a state where every service knows about every other service without hard-coding it in or doing broadcasts over the entire network? There is an interesting new protocol called SWIM, which stands for Scalable, Weakly Consistent, Infection-Style Process Group Membership Protocol, which is as cool as it sounds. So this is kind of a research project for solving this problem of how do you have universal knowledge without the exponential problem of transferring all that knowledge. This protocol works. It's actually used by Uber. Uber have taken it to 2,500 microservices, which is a pretty robust test of the underlying protocol. The basic idea is really simple. So imagine a new microservice joins the network. In a naive implementation, you send a message to every other microservice saying, here I am. With the SWIM algorithm, you don't do that. You connect to one other microservice and you say, here I am. And that microservice sends the message that you exist to a random subset, a small random subset of everybody else. So it infects a few neighbors, and then they infect their neighbors, and so on. And if you design the algorithm right, you get convergence, that is, complete knowledge across the network within a couple of hundred milliseconds. This has another interesting effect, and it's one of the massive benefits of this protocol. Normally, if a service goes down or starts responding slowly, you have timeouts. So you're going to wait 30 seconds before you kill it, before you know that service is dead, don't talk to it anymore. The problem is, in those 30 seconds, you're dropping requests. You still have an invalid information. And the problem is, if you're heartbeating that service from a central service registry, you only have one data point. You only have one thing sampling the health of the system. With this protocol, every service is sampling continuously, randomly, every other service. So if, let's say, 30 services all decide in the same tick that a given service is dead, there's a really high probability that it is dead. You don't have to wait 30 seconds. So you can fail dead services very, very quickly. So you can add services and remove them, spread that information to the entire network within a couple of hundred milliseconds, up to hundreds of services, which is awesome. It's almost magical when you see it in action. Graphically, the way the protocol works is these pings that randomly choose a subset of the network, the pings that check the health, are also used to piggyback information about the state of the system. So in this diagram, the orange server, the orange node is checking a couple of other nodes. But as well as that, the pink node has joined the network, has announced itself to just one other node. And that information about the new node is now being disseminated, infected into a small subset of the network. And then will get propagated out. So if I'm a microservice and I respond to a particular endpoint, I join the network in this way and I say, hey, I handle the /users endpoint. And that information, within a few hundred milliseconds, is spread across the network, a network of hundreds of microservices, without having a central registry, without having to do any configuration. The flip side is every microservice needs to have a small client library that knows how to do this. But the benefit is massive because you can get continuous delivery and you can get fast development, especially on a local machine. So if I need to write a new feature, I can write a new microservice, inject it into the network, and it just becomes available. I don't need to add in configuration. I don't need to say this thing needs to be found here. It's just available. And it lets you use a programming model, a design pattern that we find really effective with microservices, which is start with a general microservice that implements general but shallow functionality. And then for every new feature or for each slightly deeper piece of functionality, add a new microservice that deepens your system. And if you have the whole system running and you're just adding new microservices, you're not building technical debt because you're not expanding and complicating data structures. You're just adding small pieces of new code all the time. So there is a demo system that shows this in action. It's composed of about 14 microservices, and it is yet another Twitter clone, which seems to be the the fashion this evening. I'm just going to take you through the functionality of the system and how it's put together in terms of microservices, and then do a little code demo as well. So this system implements a really, really simple version of Twitter. You don't have to log in. You just say whatever your username is /foo here, and you are that user. So if I'm user foo and I post a tweet, that goes into the system. If I then look at my own tweets, it'll show me a list of the tweets that I've sent. If I'm another user and I search for a particular tweet, it'll show me tweets that other users have made. If I click the follow button, I'm following that user. And if I then load my homepage timeline, I see tweets from that user. And if I add my own tweet, it'll get integrated into the timeline. And if the other user, which isn't following, if you look at foo isn't following bar, so foo only sees their own tweets, but bar sees the tweets of foo as well. This system, these 14 microservices, are actually implemented so that it can scale to billions of users, which is kind of weird for a small demo system. But instead of taking a direct approach where you do a join when you want to show the timeline of users, this actually follows one of the architectures that Twitter themselves used. There's a website, highscalability.com. I don't know if you guys know it. It's pretty cool. And about 3 years ago, there was a series of articles about how Twitter was solving their scalability problems at the time. So I can't speak about how they do it now, but 3 years ago, they were using an approach called a fan-out architecture, where whenever you posted a tweet, that tweet would be injected into all of your followers' timelines. So you can see that is a message architecture, a ready-made message architecture, because as soon as you post a tweet, emit a message to the world that says, this is a new tweet, it has to go into the appropriate timelines. Okay, so what does a message like that actually look like? In this example, there's a search interface where you can search for tweets. So from a microservice perspective, everything is just messages. This is what the message looks like. It's just a piece of JSON. The reason I'm focusing on the messages first rather than the services is because that's actually the way that we design systems. When we started off with this approach, the question was always, well, what services do we build? We're going to do microservices. What are the services? That's a really hard question to answer in advance. It turns out that there's a much simpler approach, which is informally specify the system in terms of its activities. And most of those activities map directly to messages. And you end up with a list of messages that you can then group into services. So this message, which is a simple JSON document, is the piece that is the message that encodes the activity of searching for tweets. And here's some more potential messages. And what I've done is take this idea of pattern matching and applied it to the JSON documents, because if I see a JSON document that has post entry as one of the attributes, I know that that's a message that's encoding the activity of posting an entry, posting a tweet. So I can list all of the messages in my system. I can go from the informal requirements to a list of messages, group them together, and then I get a set of services out of that. So, for example, if we're looking at the post side of things, if I post a tweet, well, it's kind of obvious that I need a post service because I have a set of post messages. And when I post that tweet, I need to make sure that it's stored in some sort of search engine, and I need to store it in some sort of permanent storage. So I can specify my services in terms of the messages they take in, these message patterns they take in, and the message patterns they emit. You can see here, post emits an info entry. It lets the world know that somebody posted a tweet. And then the indexing service listens for info entry. And also has its own patterns. It's not particularly important what they are. The key thing here is you can analyze your system in terms of these messages. You can specify what the services do, and then a team of developers can work in parallel because all they have to implement is services that match these patterns. And it also lets you specify service interactions. So when I'm doing the search, I have a front-end search service that delivers that search page, and it sends the search query message to an indexing service to do the search. The info entry message, which gets sent out by the post service, goes both to the indexer, because it needs to index it into a search engine, and also to this fan-out service. And in this case, the message is observed rather than consumed. That's a pub-sub model rather than being an actor model. Now, this is all very well, but it's easier to understand the system in terms of diagrams. So another way of looking at this is to say, what are the message interactions between microservices? This is where the programming model, this is where the weird programming model gets in, because when a service interacts with another service, it's either synchronous, you expect a response straight away. That is, show me the page that lists all the tweets. Or it's asynchronous, like info entry, which says, somebody's posted a new tweet. Whoever's interested, do whatever you do. Index it into a search engine, add it to the timelines, whatever. So messages can be observed and consumed as well, and which gives you kind of 4 options. So you can analyze your system in terms of these message interactions. If we look at our microblogging system, our Twitter clone, when requests come in, we have a front service that is essentially just a proxy. And it proxies the requests to individual services that serve individual pages. So there's a home page, there's a search page, there's a mine page, which is just a list of my own tweets, and there's also an API server, which could be Nodal, right? That front service distributes incoming messages, which means that you can change the search functionality without affecting the home page. This is the whole point of microservices. You can individually deploy these things. If you were testing a new search functionality, you could deploy a new version of the search microservice and have the old one lying around, and then 50% of the traffic goes to one, 50% goes to the other, and you can measure the results. It's really, really easy to do things like that. So let's break down these services. The home service sends a timeline list message to the timeline service. The search service sends the search query message to the index service. The mine page sends a store list kind query message to the entry store. So you can see I'm sort of arbitrarily creating namespaces for myself. In practice, you don't actually need to be too careful about these namespaces, because you can always pattern match more specifically if you run into trouble. You can always add additional properties if you need to refine the behavior of your system. And you can also translate patterns from one to the other. So it's actually really, really flexible. The pattern matching is so powerful, in fact, that it means you don't really need strict schemas to make the system work. If you look at the API service, whenever you post an entry, it's sending that on to the post service, and then whenever you follow a user, click the follow button, it's sending a follow user message to the follow service. Perhaps the most interesting interaction is what happens after you post a tweet. So let's look at the fan-out interaction first. When I post a tweet, it emits this info entry message, and the index microservice is going to grab that and put it into its index so I can find it in searches again. But the fan-out service also listens to that message. It's a pub-sub model. Gets the list of users who follow me and injects that message into all of their timelines. And that's a very scalable model. This is why I say this structure can take you up to millions of users. Post also, so that's an asynchronous interaction. Post also, as a synchronous interaction, saves the message into some sort of database. And I've refined that operation here. In one of the previous diagrams, I just showed post saving to an entry store. But let's say I needed to add caching because my system wasn't sufficiently performant. Now, in a traditional code structure, how would you add caching? Well, you're either using an ORM or some sort of abstraction layer, or even you just add if statements in your code. The issue there is that it's a code level change. It's building technical debt. The cool thing about microservices is you can intercept messages. You can change your message patterns and add functionality like caching without changing other services. So neither the post service nor the original entry store service need to change. I just add a caching service in the middle and intercept the messages. The first question I get, and you're welcome to ask me when I'm finished, is how do you do the interception? It's actually not that important. There's a whole bunch of different strategies. The important thing is this is a component model. I've extended the storage microservice. I've added functionality to it without changing its code. And I could add validation, I could add throttling, all sorts of different stuff. I could add special case handling for different types of users. This is where the power comes in. This is what makes the microservice approach actually work. It lets you build functionality really, really fast because new features tend to map to new microservices. All this stuff obviously needs some sort of client library. This is the framework that we use. It's about 5 years old. It started off as a component model, and then we added network capability to it so that it could serve the needs of the microservices architecture, and it gives you the pattern matching and it gives you the transport independence. So I'm going to return to the example and just show you what this looks like at a code level. So hit me.
When you say that you can inject a service between two different services without modifying the code of that service, are you saying that because you have separated the code of the deployment or the architecture from the service itself? Because it seems like at some point you have to tell the service listen to that different intercepted and then relay the message.
You have essentially separated them, yes. The way that you do that actually depends on the implementation. So sometimes that means adding a new topic into a message bus. Other times that means adding a new property to the pattern and adding and then slowly changing the versions of the services so that the original client service, the originating service, now adds that attribute to the patterns. So there's different ways of doing it. It's more about having a conceptual model that you intercept messages and then extend functionality that way. So what I've done here is I'm using a tool called Fuge. There's links on the last page of my slides. So when you're running a system of microservices, there's a whole bunch of different node processes to run. Doing it manually kind of sucks, so it's nice to have a tool that lets you run all these different things. So here's all the services. If you go to GitHub, you'll see these are all in separate folders. And these implement the system. And you can see the front service and the home service and the mine service and all that sort of stuff. This is a happy application. But it uses Seneca for the business logic. So let's look at the search interaction. And we can see how the messages flow and how the system is put together. So if I load up the homepage for user food, there's nothing in the system at the moment. This is my development system. It doesn't have a persistent data store. I'm only storing the data in memory. When I go to production or staging, I can use a persistent data store without changing my code base because the data storage is represented by messages. And locally, the microservice that provides the storage just does in-memory storage. But in different contexts, I can use Postgres or whatever. And in fact, this entire system, because it's a demonstration system, only runs in memory. And even the search index, I don't use Elasticsearch, I just use an in-memory search index. But I could use Elasticsearch if I wanted to. So I'll just add an entry, and then I will go and search. Now, I added the entry as user foo, but if I search as user bar, you can see that the AAA entry that I put in comes up. Interestingly, this entire system is written as an old school post and redirect app. It has no client-side JavaScript whatsoever. So I thought that'd be kind of fun as well, just to do things the way we did them kind of 15 years ago. It makes it easier to understand as well. I don't have to choose between React and Angular and all that sort of stuff, or use Babel or TypeScript. Okay, so if we take a look at some of the logging output that happened, I've just set up the system. I pre-configured it so that I can see some of the activity between the search microservice and the index microservice. The search microservice serves that search page, and the index is the search index. So when the post microservice saves my tweets, it emits info entry, which is this line here. And then you can see that the index service captures it and stores it. When I perform the search, so let's just set it up again. Okay, so when I perform the search, the index service gets the search query in. You can see the query here, performs its work, and then returns with whatever the result is. And those follow lines are an extra bit of business logic that I have to mark each tweet as somebody that I've either followed already or not followed. And if I haven't followed them, I need a follow button. Each line in this log represents a message that flowed through the system. So what's interesting about this architecture is it's very, very easy for me to add new services. So if I take a look at my process list again, you can see I only have one instance of the search microservice. But if I need to scale up, I can say start search. And that's going to start up yet another instance. And you can see 2 instances are running now. So if I perform the search, it's going to act as it did before, but you notice that this is the process ID of that particular search service. And if I perform it again, you can see that it's different. So I have 2 instances running now. And what the swim algorithm has done is the new search service has registered itself into the network. And the front service has full knowledge of the network. So it now knows that there are 2 search services, and the default behavior is to round robin between them. I could mark them as a pub-sub interaction, in which case it would send it to both services simultaneously. So without having set up Kafka, anybody set up Kafka? That's kind of fun. Or without having done anything in my code, I've moved from an actor model to scalable round robin, or to pub-sub, or to any different interaction that I want. I could implement that interaction just as a JavaScript function with a bit of logic. This is where it gets really nice, because it's really, really easy to change those interactions without having to make decisions about pieces of infrastructure in your system. You get other nice stuff. So there's a REPL associated with the system. REPLs are cool, right? You REPL into your system and you can do stuff. Except the REPL in this case is yet another microservice. So you can see there's a REPL microservice, which is exposing an interaction with the system. And I could do things like, I'm submitting messages into the network. I'm not sending a message to a particular microservice. I'm just sending it somewhere. So I could say, search query, and I can get back a result. There's a really interesting message that I can send to the network, which is, I can ask the REPL service to tell me about its universal knowledge of the system. And what I've got back here is a list of every microservice and all the things that they do. And you notice that some of them are JSON patterns, but some of them are routes. So this model works not just for Seneca, but there's a Happy plugin that provides this for you as well. And you can see here is one instance of search user, and there's the second one. There's 2 instances of the search service in the system. Okay, so then what does that look like from a code perspective? The front service, when I want to search, I just say my handler is whoa. So whoa is the happy plugin that does this swim algorithm stuff. And you can see I provided it with no configuration. I didn't say you can find the implementation of search at this location, at this IP import. If you look at, so whoa is essentially a adaptation of one of the proxy handlers for happy. And normally, for a proxy, you'd have to say, where's my remote? What's the location of the remote endpoint? You don't have to here. There's no configuration, because the network will determine what the configuration is. So I'm proxying my request through to the search service. And all that does is start sending messages into the network. So we're now in the kind of private space behind the firewall. So there's that follow list message that says, get me all my followers, because I don't want to have follow buttons if I'm already following people. And here's where I submit the synchronous message that says, perform this query. And that query is implemented by the index microservice. And if I look at the index microservice, I actually have it implemented in two different files. One is the logic. So I'm using search index, which is a node module that does in-memory. It's kind of like an in-memory Elasticsearch. And here's my implementation of search query, which just does index.search with the query term and returns back whatever the hits are. You can see some of the other message patterns that I implement. Search insert, which is called when you post an entry, is just adding something. It's just adding the tweet to the index. And there's a little initialization message, which just constructs the database. More interesting is the runtime configuration, the script that actually starts up the service. And you would have different versions of this for development and production and staging. But in our case, it looks like the following. This is kind of the heart of using this approach and what your code ends up looking like. So the bases are the well-known starting points. I can add a microservice to the system by pointing it at any other microservice, but I have this bootstrap problem where I need to have an initial set of well-known services. So we tend to run a base service on each machine. And that's a hard-coded list, or a list that you can find from a traditional service registry like console. You need a way to get started. You need to find the first microservice to talk to. And after that, it's easygoing because you get universal knowledge. I'm loading up the index logic, which just defines my messages. And here's something interesting. Info entry was not a message that I defined in the search logic. I'm staying very decoupled. So messages that the post service emits are info entry messages. Messages that the index service understands are search insert messages. And they're totally different. But it's actually very simple to, as part of a runtime configuration, capture info entry messages and just translate them into search insert messages, which is what my system understands. I can define a set of patterns for the search index and then have multiple other microservices down the road for requirements I don't even know yet, emit different messages, and just translate them into the messages that I need. And then the magic piece is the mesh plugin, which implements the swim algorithm. And I'm saying, I as a microservice, the index microservice, I will respond to I will respond to any message that has a value for the search property, but I will consume that message and give you a response. I will also respond or observe any message that has info entry, along with any other microservices that care about info entry. That's how I capture the posts of the tweets. And I don't need to provide any configuration. I don't need to provide any network locations or information like that. This metadata is disseminated into the network. And if you look at my meshing thing here, you can see that index, for example, the REPL service knows that if it sends a search message, it's to go to the indexing service. And in fact, I'm actually exposing its actual network location. But I don't need to know that at configuration time. I don't need to know it in my own code. This is completely dynamic. And if I stopped and started that indexing service, I get a different location. Okay, that's me done. Thank you very much. And I should say that the plug, there was a stick in the tail. I'm writing a book about all this stuff as well. So if you want to go into more of the theory and all that sort of thing. So, anyway, sorry, first question.
So some people believe that the UI should be part of the microservice.
The UI, yes.
Some people believe that the microservice should be only request and response. What do you believe in, and how you handle the UIs?
So this is where you take the Kool-Aid and you put it down and you go, I'm not going to drink that. Okay, because in a lot of applications that we build, the code volume on the client side is 4 times, on average, the code volume on the server side. This is a server-side architecture, and it solves technical debt and problems like that on the server side. It lets you build server-side code really fast. It makes no claims about the user interface. Client-side coding, client-side programming, is really hard, way harder than server-side programming. There are similarities, and I mean, things like React, you could see this as kind of a reactive model. Things like React are interesting, and I think progress. The client side is a much harder problem. Microservices don't buy you a huge amount there, and in fact, if you're not careful, they introduce massive security risks, because if you have messages, external messages, mixing with internal messages, that's just a world of pain. When we build systems, we build a traditional REST API, type of thing you get with Nodel, and translate those into internal messages. And that's the approach we take. And we just accept client-side is hard.
So do you think microservice is replacing the SOA kind of pattern on the server side?
Yes, yeah. But it's not just, take the large services, the large SOA-based services, and make them really small, but they're still REST endpoints, because you still have that tight coupling. You've got to solve this service discovery problem. That's where you get the real benefit. That's why a lot of people end up using message bus architectures, because topics are weak identifiers, and you get a lot of the benefits without running into problems. But the peer-to-peer approach is even better.
So you're showing up your library. Is that just running inside the node process, does all the discovery itself?
Yes.
And so how do you do like a MySQL database? You have to put a node process in front of it?
Yeah, so with this architecture, you're completely hiding your data store. Now, that doesn't mean that you can't write a service that talks directly to MySQL, or, I don't know, uses Mongoose or something like that. Within a microservice, you're free to do whatever you like. The interactions between them have to follow a simplified message model. But the benefit for that is that you get components. You get the ability to add a caching layer, all that sort of stuff, really, really simply. It's kind of a weird thing. It's this principle of least power. If you look at Unix command line tools, they have a really simple API of streaming text, which means you can compose them together, right? So you can write complex pipelines that do all sorts of interesting things. The reason it works is you have this really simple API between the Unix tools. The pattern matching gives you something similar. It's a bit more complex, but it's still really simple and simplistic, which means that you can compose services together. The moment you start exposing complex behavior, traditional object components where you have to do dependency injection and there's properties and methods and all that sort of stuff, you lose composability, which is the big benefit of the service. Does that answer the question? Sorry, I kind of wandered off into a different place.
So it's saying that, if you need to know the IP address of your MySQL server, like, how do you
Oh, okay. That's a different class of problem. So in production, yes, we have console sitting there, and console knows the location of MySQL. But there's a big difference between MySQL, which maybe has like a read-write master and a couple of other read shares, and that's a small number of services. And I use the word service in a very general sense there, versus hundreds of small node processes, which is a different type of problem. Console is really good for that, but not so good for having hundreds of services. You win.
So if you're a solo developer and you're like, I want to do this, I want to use this, I want to implement this. You didn't talk too much about the infrastructure layer. What's the overhead for actually like setting up and deploying? What type of system are you using?
Yeah, that is a major cost. So you can't do this stuff without automation. You need to be thinking, yeah, we're going to use Docker Swarm because it's a relatively small system, or if it's a big system, we're going to have to use Kubernetes, or HashiCorp's Terraform is another good option. If you want the benefits of rapid development, and you want all the benefits of being able to just get continuous delivery and write a new microservice and deploy it in the afternoon, you need the automation in place. That said, for local development, things are much simpler, which is why we wrote that Fuge tool that I was showing you there, because that's just it's just manipulating 10 or 20 processes on your local machine. You don't need to run hundreds of instances. You just want to run a couple so you can test the interactions.
Kind of a little three-part question. One was, what's the transport that's being used for communication between different microservices right now? How do you change it, and
Yeah.
do you have multiple? Or is it one person?
Yes, you can. So it wouldn't be much of a component model if it didn't have a plug-in architecture. Transport independence is a key principle. So in the example that I'm showing you there, if you run that code base, it's point-to-point HTTP, which is what I've just been telling you not to do, but because I've hidden the identity information, it's suddenly safe. But if you look at the plugins for the Seneca library, there's transports for Kafka and RabbitMQ and Redis and even streaming TCP. Basically, so long as you just want to get a JSON document from one place to another, and anything that can carry your pigeon doesn't matter. Anything that can transport that document over works as a transport.
Is it possible to have a multi-transport?
Oh yes. So yes, pattern matching is wonderful. I can say for messages that match this pattern, transport them over Redis, and it's a pub submodel. And for messages that match this other pattern, well, they go over RabbitMQ, and it's a work queue. And for these other ones, because I need speed, actually, they're like streams.
And that's specified in configuration on the server?
So that is specified here. So this is why there's a little script that defines what the service looks like. So instead of using the mesh transport, for example, for those things, I could say .clients type is Redis, and that would send all those search messages over Redis instead. But of course, I'd have to know up here. I'd have to go, yeah, you know what? I'm going to have to use Redis transport, and I need to put in my configuration. And I mean, I could have multiple ones, so I don't know. This one could be HTTP, and that's where info entry goes.
How this works with containers like Docker and all that stuff?
So yes, that is a really good question. We use Docker a lot. This particular example does not address deployment issues at all. But if you go to the GitHub repo, there's a link to another example system called Nodejs, which is a search engine for node modules. And that system is simpler. It only has 7 microservices, but it goes all the way from the stuff that I've done here on local development all the way up to actually deploying it. And nodejs.com is currently running an old version of the system, but in the next week or two, we're actually going to upgrade it to run a full microservice system. Part of the reason we do that is, so we're consultants, so a lot of the stuff we do we can't talk about. So we thought we'd kind of build example systems small example systems so people could understand how the bits fit together. And the Nodejs example is end-to-end, all the way up to production.
And API gateway, do you use API gateway also?
We mostly use Happy for those types of problems. Happy is well, it's performant and proven in production at very, very high load. We're pretty happy with what it does.
Back on the transport question.
Sure.
What kind of transport do you use for service auto discovery? So, like, obviously sending messages.
Oh, yeah. So how does the swim algorithm?
Pluggable, but what, like, how do those initial sort of like posts find each other?
So the particular implementation that we use uses UDP and multicast. So that causes you a particular problem with Docker containers because you have to use host networking for this to work, which is a little gotcha at the moment. Thank you very much, guys.